Alright, welcome to the Autumn 2 Week 6 exam video for Year 11 on the subject of the properties of waves. So, you can see the first question right here. It talks about the diagram of a longitudinal wave on a stretched spring, and it asks us to use the bold words from the diagram. Now, it have to be from the diagram to be correct to complete the sentence. So a longitudinal wave is one in which the oscillation, so picked from there, causing the wave is parallel to the direction of energy transfer. So it's got to be those two words. Anything else is not going to get you the marks. So 1 mark for each correct word. Now you can see the second part of the question I've actually crossed out, and that's because this is an old question based on the old GCSE syllabus, so you do not need to worry about it at all, so just cross it out. Then on to part B. So the diagram shows water waves made by a wave machine in a swimming pool. Every second, 2 waves go past a person standing in the swimming pool. So the reason I've underlined these things is because we are going to need to work out the speed of the wave, and to work out speed of the wave we need to know the frequency. Now those two things give us a real clue about what the frequency is, because the definition of frequency is the number of complete waves passing a point per second. And this tells us that 2 waves go past a person every second. So what that's telling us is the frequency is 2 hertz. So we know that from that sentence. So then over the page, we're then told that the waves have a wavelength of 0.8 meters, and we have to find the speed of the wave. So following the normal format that we always do for equations, you've got the 3 things written down. So V we don't know, but it's in meters per second. The frequency from that sentence is 2 hertz, and the wavelength is 0.8 meters. Then our wave speed equation, V is equal to F times lambda. So V, the speed of the wave, is equal to 2 hertz times the wavelength, 0.8 meters, which gives us a velocity of 1.6, and then the unit of wave speed is meters per second. So you get 2 marks for having the correct answer, 1.6, and 1 mark for the correct unit. Okay, on to part C. So the graph shows how the speed of deep ocean waves depends on the wavelength of the waves. And we're asked, what can we conclude from the graph? So the key thing about this graph is we should notice that there are 2 sections to the graph. We start off in the first maybe 60 seconds with a really steep curve, so quite big changes in wave speed as we increase wavelength, and then as we go to higher wavelengths we are still getting an increase, but the curve is flattening out, so the increase in wave speed is not as big. And that's the 2 things we really have to describe and conclude from the graph. So the first key point, that what this graph is showing us, the relationship between wavelength and wave speed, that as the wavelength increases, the wave speed increases. That's key point number 1, and we can see that from the fact that the line is going up. Then to get your second mark, you need to give a bit more depth to this. So wave speed increases faster between 0 to 40 meters than between 100 to 140 meters. Now, that's me making it really clear that there's a fast increase at the start of the graph between 0 and 40, and then a slower increase in wave speed at higher values of 100 to 140. You don't have to explicitly state values, but you need to make it clear that there is a change, so that for higher values of wavelength there is a smaller increase in speed. Okay, if you've done those 2 things, then you will get yourself the 2 marks. Okay, on to question number 2. So, it says the diagram shows a water wave drawn to scale. And we're going to have to find the wavelength and the amplitude. So you can see that I've drawn onto the graph ways of finding those things. So the wavelength first. Remember, wavelength is the distance from one point on a wave to the next identical point. So I decided to choose the crest of the wave right there to the next crest. And we can see that this crest is at 0. This crest is at 4, so the wavelength is 4 centimeters. Now to find the amplitude, key thing is it's the distance from the rest position, and you can see I've added in blue, I've actually added in the rest position, so I can see really clearly where it is. So it's the distance from the rest position to the crest. And so if you measure the vertical distance using the axes, that's from 0 up to 3. So the amplitude is 3 centimeters. So 1 mark for each of those. Okay, then 2C. So 12 waves pass an observer in 4 seconds. We have to find the frequency of the waves. So again, we've got a couple of key things here. 12 waves passing in 4 seconds. So remember, the definition of frequency is how many waves pass a point per second, so in 1 second. So we know that there are 12 waves in 4 seconds. So if we want to find out how many waves in 1 second, we need to divide both of these numbers by 4, and that's going to give us 3 waves in 1 second. So I get 2 marks for having 3, and then 1 mark for having HZ, hertz, the unit. Okay, then we're on to question number 3. So, waves may be longitudinal or transverse. Describe the differences between longitudinal waves and transverse waves. So it's a 3-mark question, and the first part of the question, the first thing you need to do to get the first mark is to use either the term oscillation or vibration. You must use those words in your answer. So if you've used one of those terms, you get a mark. Now, the second mark is then for picking out what is either a longitudinal or a transverse wave. So I've done the transverse wave first. So where the oscillation or the vibration is perpendicular to the direction of energy transfer, that's for a transverse wave. So I'm going to get my second mark for that statement. And then my third mark is for saying that the oscillation is parallel to the direction of energy transfer for a longitudinal wave. So 1 mark for using either of those terms, 1 mark for the idea that in a transverse wave the oscillation is perpendicular to the direction of energy transfer, and the third mark for in a longitudinal wave the oscillation is parallel to the direction of energy transfer. Okay, on to part B. So, tells us radio waves are electromagnetic waves. Describe how radio waves are different from sound waves. So you could do two things here. You can either talk about radio waves or you can talk about sound waves. So I have split each possible marking point, and there are 4, into 2 ways of saying it. So for the first point, saying that radio waves are transverse, that gets me a mark. Or I could say that sound waves are longitudinal, that would get me a mark. But, and this is crucial, if I said those 2 things, I do not get 2 marks. Right? It's 1 mark for either that or that. Second possible mark, so radio waves travel at a higher speed or sound waves travel at a lower speed. Now if you said radio waves travel at 3 times 10 to the power of 8 meters per second, so let me just add that in. So 3 times 10 to the power of 8 meters per second, that's the speed of radio waves. If you said that, that would be absolutely fine, because sound waves travel at a much lower speed than that. But the key thing is that they are traveling at different speeds. Then your third possible mark, so radio waves can travel through a vacuum, or you could say sound waves cannot travel through a vacuum. And your fourth possible mark, that radio waves are electromagnetic waves, whereas sound waves are not electromagnetic waves. So you've got to pick out that difference. So either one of those statements will get you your 4th mark. Okay, then on to question 4. So it says a sound wave is an example of a longitudinal wave, and in figure 1 we've got the air particles in a sound wave as the wave travels from a loudspeaker to an ear. So be careful not to miss questions like this, because there's no lines to answer, but it's asking us to write a letter R on figure 1 to show an area of rarefaction. Now remember that a rarefaction is where the particles are spread out. So where the particles are spread out, we can see there, 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 and there. So putting an R in any one of those will be fine. I've put them in all the possible locations, but any one will be fine. And then, just as a quick reminder, that area there where the particles are close together we call a compression. Alright, so where particles are close together is a compression, spaced out is a rarefaction. Let me just make sure that's nice and clear. Okay, then we've got for 4b a sentence about longitudinal waves. So the vibrations of the air particles are parallel to the direction of energy transfer. Just the key definition of what a longitudinal wave is. Then 4C, so a stationary car horn emits a sound wave of frequency 400 Hz. The wavelength of the wave is 0.85 meters, and we've got to calculate the speed of sound. So again, that wave speed equation, so frequency is 400 Hz, wavelength is 0.85 meters, wave speed is frequency times wavelength, so 400 times 0.85, and that gives us 340. This time we don't need the unit, it's already there, so 340 gets you the 2 marks. Okay, on to question 5. So, infrared and microwaves are 2 types of electromagnetic radiation. State one example of the use of each type of radiation for communication. So it's got to be for communication. You can't give the other uses of infrared or microwave only uses for communication. So for infrared, you can either say for a remote control, or you could say in a fiber optic cable. If you just said fiber optics, that would be fine, but one of those to get your mark for infrared. And then for microwaves, you could talk about using them for mobile phones, or for satellite TV, or for Wi-Fi, or for Bluetooth. So one of those 4 for the second mark. Right. Over the page, then to part B. So some of the properties of infrared and microwaves are the same. Now, I've written a keynote here. Remember, they're both electromagnetic waves. So properties that are the same are things that are in common with for all EM waves. And we have to pick out 2 of the properties. Now you can see I've put absolutely loads down here. So they've got the same speed, and if you were specific, saying that they both travel at 3 times 10 to the power of 8 meters per second, that's fine. They're both transverse, they both transfer energy, they can both be reflected, or refracted, or absorbed, or transmitted, and then my final one is that they can both travel through a vacuum. So to get the 2 marks here, you just needed 2 of those options. And then our final question. So we've got a question with about electromagnetic waves, and we've got to use our wave speed equation again, but this time we're interested in frequency. So we're going to have to rearrange the equation. So let's get down what we know. So V, the speed, 3 times 10 to the power of 8 meters per second. F is what we want to find. Remember, the unit is Hertz. And then the wavelength is given to us. It's 2 centimeters. But that's not the standard unit for wavelength, so we need to convert it into meters by dividing by 100, which gives us 0.02 meters. Then we got our wave equation, V equals F times lambda. So V is the speed, 3 times 10 to the power of 8 is equal to F times the wavelength, 0.02. And then to find F, we're going to rearrange it, so we're going to divide both sides by 0.02. So the frequency is going to be 3 times 10 to the power of 8 over 0.02, which gives us a speed of, in standard form, 1.5 times 10 to the power of 10, or it's acceptable to give the non-standard form answer. So we got 15, and then we've got 9 zeros after it. So either of those is fine, and that's what we need for the 2 marks. If you forgot to convert the 2 centimeters into meters, you could still get 1 mark for following the rest of the steps fully. Okay, that is the end of the week 6 exam video.